We've all been there. You're on the games console. Comfy chair? Check. Drinks and snacks? Check. Having one of your best runs ever? Check. And then, disaster. The ghost in the machine decides it's time for some payback for the demise of all his electronically generated buddies. He takes control of your console, and your controller no longer responds quite how it should. The steering doesn't work on your car game, the targeting is off on your first-person shooter, your racket doesn't move quick enough in your tennis simulator. The red mist descends. Somehow, the controller is now speeding its way towards your most recent big-ticket electronics purchase, the 4K TV. Time slows to a crawl as the controller gets ever closer, which gives our intrepid designer Johnny time to run a quick analysis to see what's about to happen to his TV screen. Johnny puts together a quick assembly with a TV and controller. Johnny is interested in what happens to the screen. It's the TV that's expensive, and not the controller. He simplifies his geometry by removing the casing of the TV and defining the TV screen as 3 thin layers defined as surface bodies. These layers are the glass screen, a layer for the polarization filters, and a layer for the electronics board. He also simplifies the controller as a disc the same size as the end of the controller, which is about to hit the screen. While Johnny can't show pieces of glass breaking off the screen, he can set the material stiffness to be very small when it reaches a critical stress. To do this, he chooses a nonlinear analysis, and as he is working with a fast-moving object, he chooses the dynamic option. Johnny defines a thickness for each surface body and defines materials properties using the von Mises plasticity model, where, as well as an elastic modulus, Johnny defines the yield stress and the stiffness of the yielded material, which is set very low to simulate the broken screen material. Johnny gives the disk representing the controller an initial velocity of 5 meters per second, and then meshes the study. He adds a small initial time step, and because he needs to consider that some material in his model will have a very low stiffness, makes sure the large displacement and large strain options are turned on, as well as increasing the maximum strain increment to 25%. Johnny runs the analysis. Johnny looks at the stress results and animates the response. He can clearly see the impact point, and the area around the impact point quickly exceeds the yield stress of the glass. He can also see the shock wave passing through the screen and the interference patterns caused by the reflection of the shock wave off the edges of the screen. Johnny looks at the stress results and finds the point in time that the glass reaches its yield stress of 31 megapascals, about 0.0085 seconds. He then looks at the displacement results and, using the time value, looks at the displacement value at this point in time, about 2.25 millimeters. Finally, Johnny looks at the reaction forces. At the point in time where the screen breaks, the reaction force at the edge of the screen is relatively small. As the shock wave in the screen progresses, the forces at the edge of the screen increase significantly. What can Johnny do? The TV screen is just so fragile. Toughened glass, protective cage. How about a wrist tether? $3.99 at a well-known online retailer. Sometimes the best solution is the simplest one. To learn more about SOLIDWORKS simulation, contact your local reseller or visit solidworks.com/simulation.